Okay, we're going to start chapter 5 today. Chapter 5 is all about projectile motion. So in this video, we're going to go over what a projectile is and some of the variables that we'll need in order to solve physics problems involving projectiles. So if you look at this picture, this animation on the screen here, this guy's shooting the bow. The arrow would be the projectile. And if you look at this animation down here, the cannonball that's being shot out of this cannon is also a projectile. So please be following along in your chapter 5 guided notes as we go through these slides. So first thing that you need to know is what a projectile is. And so in your notes, I've got a spot for you to write down the definition for projectile. A projectile is any object that moves through the air or through space, acted only on by gravity. Okay? So it's any object that moves through air or through space, but a projectile is acted only on by gravity. So, for example, like an airplane would not be considered a projectile. It does go through the air, but it's being propelled through the air by an engine. Or a helicopter is not a projectile, because again, it has an engine that is propelling it through the air. And so projectiles are going to be things like a football after you throw it or kick it, a golf ball after it's been hit, or a rock if you throw or drop a rock. So it's any object that is just being acted upon by gravity. So there's different types of projectiles like this picture shows here. This person is just dropping a rock off of a cliff. And so after it leaves the person's hand, the rock is only being acted upon by gravity. And same in this situation where he throws it up and the ball comes back down. Still a projectile. And even if you throw it up at an angle, it is still a projectile because gravity is the only thing that's acting upon that object. So projectiles near the surface of the earth follow a curved path. And this is due to the force of gravity. To illustrate this point, if this cannonball that's being shot out of the cannon, if there was no gravity acting on it, after it's shot out, it would follow a straight path, horizontal. So this is the gravity-free path. But we know that that's not the case in a real-world situation. So what happens after you shoot the cannonball is that the cannonball is going to be pulled on by gravity. But when you look at the path that a projectile makes, it kind of makes this curved path. And I wanted to point out a couple of things. Horizontally, if you look at the horizontal interval here, if you look at it as it progresses through its path, horizontally, the distance between these intervals is the same. And so that's one thing to notice. Let's look at the vertical path, and you'll notice it's much different. The interval is very close together at the beginning of this cannonball's flight, but at the end, you'll notice the intervals are spaced out farther apart. And the reason for this is because gravity is an acceleration, and it accelerates things a negative 9.8 meters per second squared towards the center of the Earth. And so because it's an acceleration, you'll remember the ticker tape diagrams. As the cannonball is speeding up as it falls, the distance becomes greater the more time it spends in the air. And so that's why you see a curved path, and it looks like that. Okay, so that curved path has a name. It's called a parabola. So I think there's a spot in your notes to write down the definition of a parabola. A parabola is a symmetrical rainbow-like shape that a projectile follows in the air. And you'll notice that whenever you have a projectile, whether it's a football being kicked, like this example, this punter is kicking the ball, and it follows this rainbow-like shape, we call it a parabola. Well, a golf ball that you hit off a tee would follow the same kind of parabola-like shape. Or if you throw a rock, or any other projectile is going to follow that path. Okay, a parabola is a graph of a quadratic function. Because it's a quadratic function, if you were to graph y is equal to x squared, it's going to follow the same sort of parabola-like shape, and that's the reason. It's a quadratic function. So I've got this video that I have put on the YouTube page, but it shows the path of a projectile. So it's got this wooden structure you see here, this wooden structure. But as you're going to see, when this projectile is launched, it's not going to be on this wooden structure. It's going to be above it. But it will help you see the path that a projectile will take. So let me hit play, and I think it's in slow motion, so you'll be able to see it. And so, yeah, even though that projectile is not touching this wooden structure, we definitely could see that it was following that parabola-like shape. Okay, so we said that a projectile was something that's being acted upon only by gravity, and that's not 100% true. There is air resistance that's going to influence a projectile. So air resistance is the friction due to air that a projectile will encounter as it flies through the air. All projectiles will feel this air resistance. But in all of our projectile motion problems that we're going to work in this chapter, we're going to neglect air resistance, which means we're going to ignore it. And so our problems aren't going to be 100% accurate, but they're going to be pretty close. So why are we going to ignore air resistance? And the answer to that question is air resistance is very complicated and complex to calculate, because projectiles have different shapes. You would have to calculate all the curves, and it would be way too complex for this first year physics class. And so we're just going to make it easy and ignore air resistance. But just realize the calculations that we do, they're going to be pretty close. But the projectile is not going to fly as far as we figure that they will fly because we are ignoring air resistance. All right, this is an animation that shows the path of a projectile as it flies through the air. The path of the projectile is this blue path, and you'll notice it forms that parabola rainbow-like shape that all projectiles make. But again, I wanted to go through this green path is the horizontal path of the projectile, and notice that the intervals here are evenly spaced out all the way through the projectile's path. And so that is because the constant, or the horizontal motion of a projectile is constant. We are ignoring air resistance, so it's not going to be slowing down in the horizontal direction. And so every one of these intervals is equal distance apart. Now let's contrast that to the red path here, which shows its vertical, a projectile motion's vertical path. And you'll notice that the intervals, as it falls toward the earth, get more and more spaced out. They're very close together up here. By the time that projectile has fallen through the air, that interval is quite a bit larger at the bottom. And again, that's because there is acceleration down. And so it's speeding up as it falls. Where the horizontal, we just see its constant motion. Okay. All right, so here's an animation that kind of illustrates that point. If this truck was moving at a constant velocity, so let's say you had it on cruise control, and you launch this projectile in the air from the bed of the truck, as long as the truck is going at a constant velocity, when you launch that projectile, it will come back down and land in the same spot it was launched from. And the reason for that is because horizontally, the projectile has constant velocity. And if the truck is moving at constant velocity, they're going to end up in the same spot. But let me ask you this. If the truck was to accelerate after you launched it, so let's say you hit the gas pedal after this projectile was launched, then the truck would be ahead of the projectile, and the projectile would land behind the truck. And just the opposite is true. If, after you launch the projectile, you hit the brakes or decelerate in that truck, then the projectile is going to hit in front of the truck. So again, that just kind of illustrates the point that if you are moving at constant velocity, because projectiles also move at constant horizontal velocity, then they will line up when it lands. Okay, and here's another animation of that point as well. If this airplane was moving at a constant speed or a constant velocity, and you were to drop something out of the plane, notice the projectile and the plane are in the same spot because they are both moving at constant velocity. So, just another way of seeing that. Okay, so an introduction to projectile motion. So number one, projectiles have two components of motion. When I say two components, what does component mean? Well, a component is a part. So we're going to look at projectiles' motion in two parts. One is the vertical motion that it makes, and that follows along the y-axis, because vertical is up and down, and so is the y-axis. We're going to split that from its other component of motion, horizontal motion. Horizontal is left and right, so that's why we say it follows the x-axis. It's more horizontal. So we're going to split up its motion into two components, vertical and horizontal. Number two, the vertical acceleration. So vertically, so again we're talking up and down. The vertical acceleration is given this sign lowercase g. And what that means is the acceleration due to gravity. Its magnitude is a negative 9.8 meters per second squared. Any object, any projectile that we're going to experience in this chapter is going to feel that acceleration. And that's just for anything on Earth. It's going to accelerate at a 9.8 meters per second squared down. And so that's why the sign is negative, because the gravity always pulls things down. And down in physics, we said was a negative sign. Okay, number three, the horizontal component of velocity. So we're talking about the projectile's motion left and right in a horizontal motion is constant. Okay, we illustrated that with the last few slides, I think. Its horizontal motion is going to be constant. And number four, the horizontal and vertical motions are independent of each other. So we're going to study them independent of each other, which means they don't depend on each other. We'll solve for the motion horizontally, and then we'll solve for it vertically. And we can solve for those independent of each other. But they do have one thing in common. The time that the projectile is in the air is going to be the same for the vertical component and the horizontal component. Okay, here's a couple of words that you're going to probably be exposed to with projectile motion problems. One is range. The range is the change in x. So we're talking about the change in your horizontal part of motion. And in fact, we're going to call it the horizontal displacement. Remember at the beginning of the year we talked about displacement. It's the distance from where you start to where something ends up. And so, I don't know, if you're going to kick the football, say you're kicking the football, your range is the total distance that you can kick it. From the start here to where it ends up would be your range. Let's contrast that to this other word, height. Height is the change in y, and so we're going to say that it's the vertical. So the vertical displacement. So if you were to throw a rock in the air, you would start from the point at which you release it and go up to its highest point, its apex, and that is its change in y, or its height would be the vertical displacement. So range and height, we'll look at the differences between those words. Okay, again, this is kind of just a slide that will summarize what we just talked about. The path of a projectile forms in the air. So what do we call that path? It's called a projectile, and it's kind of this rainbow-like curved pattern. Again, it's caused because of gravity, and gravity accelerates things down toward the earth. What do you notice about the distance between the horizontal time intervals? So what this question is talking about, what do you notice about the distance between these intervals? And the answer is, it's constant. And that's because projectiles have a constant horizontal velocity. Okay, let's answer this question. What do you notice about the distance between the vertical time intervals? So the distance between the vertical time intervals, what you're going to notice is that the distance between them increases as the object spends a larger amount of time in the air. And that is because of acceleration. So it's going slow at first, but the velocity is increasing because gravity is accelerating it toward the center of the Earth. Okay, and this last question, are the horizontal and vertical times the same? So if this projectile, this red dot here, what represents our projectile, does it spend the same amount of time horizontally as it does vertically in the air? And the answer is yes, they are the same. I mean, it's got to be the same. Okay, I wanted to finish up with a couple of slides. I want to explain how we're going to solve projectile motion problems. We're going to use equations to solve them. And in our equations, there's going to be 7 variables that you will need to know. So we're going to go through these 7 variables. In your guided notes, I would hope that you write down these variables either on the top or on the bottom or in the margin somewhere so that we know exactly what they are. Okay, so the first variable that you're going to see in these equations is v sub f. V is for velocity, and this little sub f right here is for velocity final. So this is the velocity that that projectile has at the end of its time in the air. So velocity final. Number 2 is VI, or velocity initial. The I stands for initial. In some physics textbooks will write it like this, a V and then a little circle right there, or V naught is what they call it. That just means velocity initial. And if we're talking about velocity, the units are going to be meters per second. Remember, we're always in the metric system. So we're not going to use miles per hour, we're going to use meters per second. Okay, number 3, T sub F is for time final. That's the final amount of time that the projectile spends in the air. And number 4 is TI, which means time initial. Okay, so the time that it starts is usually 0, unless they tell you otherwise, and time final will be the amount of time that it's spent in the air. For time, the units are going to be in seconds. Number 5, the 5th variable that you're going to see in these equations is d sub f. D sub f is for displacement final. That's how far away that projectile landed from where it started, and that's d sub f. Okay, and then number 6 is d sub I, which is displacement initial. And the units for displacement, as you'll remember, we've talked about this before, the units for displacement is meter. So it's just m for meter. Again, we're using the metric system, so we're not going to measure in yards or feet. It's got to be in meters. Okay, and the final variable that you're going to see is a in your equations. This a is for acceleration. In a lot of, maybe I should use this as well, but physics textbooks will use g for the acceleration of gravity. And the acceleration due to gravity on Earth is 9.8 meters per second squared. But remember that gravity pulls things down, so it's always going to be a negative 9.8 meters per second squared. Okay. So let's get to the equations that you're going to use in this chapter. Okay, and there's a spot in your notes where you're supposed to write down these equations. There's 5 of them. So if you would like to hit pause right now, jot these equations down, and then we're going to briefly go over each one of them. Okay, so let's look at equation number 1. I want to go through the variables. D is for displacement. This would be displacement final, is equal to velocity times time. You use equation number 1 only when you're considering the horizontal motion. So I would like you to make a little note on your guided notes. This is just a horizontal equation. So only use it when the projectile, when you're considering its horizontal motion, and that is left and right. Okay. The other four equations, so 2, 3, 4, and 5, these are our vertical equations. So when you're considering its vertical motion, we're going to use equation number 2, 3, 4, and 5. Okay, let's briefly go over them. Equation number 2 is for velocity final is equal to velocity initial plus the acceleration. You could put in a little g here if you wanted instead of the a, because it is vertical and gravity is pulling it down, and so maybe I should switch that to a g, times t. So you would use this equation if you don't need the displacement, because look, there is no displacement in this equation. Number 3, let's go to this one. It says d for displacement is equal to 1/2 times the velocity, this should be velocity final, plus velocity initial times time. You would use equation number 3 if you don't need to calculate the acceleration. Number 4, I want you to put a star by 4, or maybe kind of outline it. Equation number 4, you're going to find that we use this equation the most. This is kind of the workhorse equation for projectile motion problems. So let's talk about it. D for displacement of that projectile is equal to the velocity initial times time plus 1/2 the acceleration times time squared. You're going to use this equation if you don't need velocity. Okay, but again, you're going to notice as you go through these problems, we use number 4 a lot. And the last equation, velocity final squared is equal to velocity initial squared plus 2 times the acceleration times displacement. And notice this doesn't have time in it, so you would use this equation if you don't need to solve for time. Now the tricky part with these physics problems dealing with projectile motion is picking an equation that will work, that will solve for what the question is asking for. So I'm going to spend a lot of time talking about which equation. And what I do is I just go from the top. So if it's horizontal motion, we can use equation number 1. If it's vertical, we're going to come down to 2, 3, 4, 5. And then if you have only one missing variable, you can solve it. But what if you had 2 missing variables? So if you didn't know velocity final and time, you would not be able to use equation number 2. So we've got to pick the right equation, and we'll spend a lot of time talking about that in the next video as we go through some actual problems. So anyway, hopefully that helps. In the next video, like I said, we're going to start working some actual problems and using these equations and finding these 7 variables. So hopefully that helped.